today what we're going to do is look at the rational root theorem. This is our last theorem for polynomials, functions, expressions, whatever you want to call what we've been looking at. In my opinion, one of the hardest, just because we throw in some new variables now. Again, like I said, math people, sometimes we don't make a whole bunch of sense. And if you don't use this theorem enough, it won't stick with you. You'll forget it. On a day-by-day basis, if we touch it every day, it becomes pretty easy. So, without waiting, let's get right into it. Turn to page 15. Again, this is the last branch of the tree diagram, and again, it is the rational root theorem. Okay, so what rational root theorem is, it tells us to find all of the possible rational roots of a polynomial. Math 2, we looked at rational versus irrational numbers, so I expect y'all to remember that. A rational number can be written as a fraction, so I like to call them pretty numbers, even though they may be negative. It's decimals, like negative 0.5. You should be able to immediately tell me negative 1/2. If I say 0.125, that's 1/8. 3.25 is 3 1/4. Okay, so these decimals can be rewritten as fractions, or like you can say them and it sounds clean. All right, so how do we get there, or like what's its purpose? So back before you had graphing calculators and Desmos, you were expected to be able to know how to do this stuff by hand in order to tell us everything you needed to know about roots and solutions, zeros, x-intercepts of polynomials. Now with graphing calculators, these theorems have kind of fell to the wayside, and you can kind of shortcut them if you slow down and think. But so anyways, again, how do you do it? So what you want to do is you want to factor the constant term and the leading coefficient. And you want to take both the positive and negative of each factor. Again, so what you're going to do is you're going to take the positive and negative constant, divide each of those factors by every leading coefficient factor. Again, this looks kind of goofy right now. It'll make a little bit more sense. Where I was telling you that sometimes math people don't make sense, in any math book, any textbook you look at, it's going to say P over Q, where P is your constant and Q is your leading coefficient. Again, I have a hard time remembering that personally, and I teach it. Okay, so again, C is constant divided by LC, leading coefficient. Okay, now third step would be test all by using, now again, all of these theorems tie into each other. So what theorem could we use to see if a number or a value is a factor of a polynomial? Okay, the remainder theorem would allow us to take that number, plug it into the polynomial, and test it. Again, our result, our verification, is then used by which theorem? Good, the factor theorem. Okay, and we can verify by if our remainder theorem is equal to 0 or not. If, when we plug that particular value into our polynomial, if that value comes out 0, we're good, it's a factor. If not, then not a factor. Okay, so test all by using the remainder and factor theorem. Okay, so for this example, what I need to do is find every factor of my leading coefficient and my constant. Again, this is why it was so important for us to be able to break down a polynomial into all of its different pieces and parts. So, if you can't identify or you don't know what your constant term is, you're not even going to be able to get started. So your constant term, again, is what does not have a variable beside it, or the number that doesn't have a variable. All right, so this time it happens to be 60. And your leading coefficient is 3. Now some of you may ask, well, why didn't you worry with like the positive and negative sign? You can. It's not going to hurt anything, especially because what you're going to wind up doing is taking the positive and negative of each factor anyways. All right. So 60. What I like to do, again, when I was coming up in math, my teachers would make me start 1, and then I would have to put the number that paired up with it on the bottom, then I just run through 2 and 30, 3 and 20, 4, 15, 5, 12, 6, 10, 7 doesn't work, 8 doesn't work, and now I know to stop. The reason I know to stop is because if I take the square root of 60, it's between 7 and 8. Okay. So I actually tested one more than what I should have. Reason you stop, reason you take the square root, all right, is because if I keep on going to like 9, doesn't work, leaves me a decimal. 10, well, I know it's 6, but I've already used it, so like I'll just be wasting time. So what taking the square root does is essentially what number times itself. It is going to stop you from repeating. And then you just factor your leading coefficient. All right, so 3 is just 1 and 3, and I'm done. Now this is where the time-consuming part comes in, because I now have to list every possible factor, and I have to do a whole bunch of dividing here. Again, it's going to be every constant number divided by every leading coefficient. So what do I mean by that? I have 1 divided by 1, 2 divided by 1, 3 divided by 1, 4 divided by 1, 5, 6, 60, 30, 20, 15, 12, 10. All of those things divided by 1. The sad thing is we can do all of this and only 3 max are going to work. So again, this is just a guess, okay? So I'm actually going to take the time to write all of these down. 1 divided by 1 is 1. And then 2 divided by 1 is 2. Again, 3 divided by 1 is 3. 4 divided by 1 is 4. 5 divided by 1 is 5. 6 divided by 1 is 6. And this is where I become a little bit special. 60 is bigger. I like to write them in order from biggest to smallest to biggest. Excuse me. So now I'm just going to go backwards here. 10 divided by 1 is 10. 12, 15, 20, 30, 60. All right. And again, positive, negative, all of these. Well, so now I'm still not even done because I only did 1. Now I have to go back and do all of these again with 3. All right, so 1 divided by 3 is 1/3. 2 divided by 3 is 2/3. 3 divided by 3 is 1, but if you look, I already have 1, so I don't need to rewrite it if it's going to repeat. 4 divided by 3 is 4/3. 5 divided by 3 is 5/3. 6 divided by 3 is 2, which I already have. 10 divided by 3 is 10/3. 12 divided by 3 is 4, which I already have. 15 divided that by 3 is 5, which I already have. Then I need 20 over 3. 30 divided by 3 is 10, which I already have. 60 divided by 3 is 20, which I already have. So this right here is my answer for rational root theorem. Identify every possible rational root for this polynomial. And again, all of these are just possibilities. There's no guarantee they're going to work. Again, we then use fundamental theorem of algebra. What that's going to do is tell us there's going to be no more than 3 solutions. Well, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 14, 15, 16, 17. Have 18 possibilities. Okay. Now, 1 may work, 2 may work, 3 may work. The end goal here is not to waste our time and test all of these. Okay. This is where I'm saying you can shortcut these things. The way I like to shortcut them is do this. I like to take my polynomial that I'm given and just go straight to y equals and then type it in. 3x cubed plus 8x squared minus 31x minus 60. All right, and now what I'm going to have are my real roots. Okay, so my real roots, or the ones that actually work, are -4, 3, so 4, 3, and -1.667. So again, I highlighted 4 and 3, -4 and 3, excuse me. So 4 needs to be negative, 3 is going to be positive, and then -1.667. So it's got to be a decimal. It's got to be 0.667. So it's going to be something. So it's going to be one of these. And then again, if you're not good with just like, oh, quickly realizing 1/3 is 0.333, 2/3 is 0.66667. If you can't do that, no harm, no foul. Just type what you see. 1/3 is 0.33333. All right, well, what if I just put a negative? Because Mr. Harrell said I have to take both positive and negative. All right, doesn't work. So 1/3 didn't work. 2/3. -0.6667. So like that's it. So it's going to be a negative, but I need to like go up just a little bit more. So I'm going to try 4/3. -1.333. I'm still getting closer. And then if I try 5/3, -1.667. That's what I want. And again, it's going to be negative.